Okay, let's start. Good morning, everyone. Welcome to the second lecture of Introduction to Artificial Intelligence. And today we'll be talking about formal models and search as one of the most fundamental methods that you can use in AI and for solving AI problems. So, today we will cover several questions and several problems and topics. And I would like to emphasize what you will learn today and try to keep this in mind. So the first and I would say the most important part that we will cover today and we will try to discuss and I will try to convince you is that we need formal representation, some formal representation that we can use to capture some problem that we are trying to solve. For example, finding a path for a robot, or finding a schedule for some university, or finding a schedule for a factory, right? So these are all instances of a problem, and my argument today that it's good to have some formal representation of this problem. Then we will be talking about search. So how to use this formal representation in search algorithms and what are search algorithms, and today we will be talking about some instances of search algorithms and we'll continue next week. And I'll try to give you some unifying perspective on the search algorithms because you should already know some of the search algorithms, for example, from courses focused on discrete mathematics. So you should be familiar that yes, there is some graph, and on this graph I can try to find some path, right? So and I can use some algorithms to do that. And we will basically introduce some very simple unifying algorithm that covers multiple of these variants of these search algorithms. And we will start by discussing that even nowadays, even in the era of large language models and other great AI breakthroughs, search is really still relevant because many of these examples that I have on the slide, and also some others that we will discuss later, are using search as one of the components. It's not the component, so it's not that search is the only method that is used in these algorithms, by no means, but it's there. So in many of successful AI deployments, you still have search as a component, and since it's a fundamental method and one of the core methods of AI, we need to cover this and we need to understand it, because if you do the search in an incorrect way, the downside is that you will never find the solution. You will never find an answer, because inherently in AI we are trying to find a problem that is at least exponentially large. We want to find a solution in a space that is at least exponentially large, more often doubly exponential, and so on. So really, we need to understand the search algorithms, and we need to be able to use them properly and in the right way. So let's dig in. So let's start with a discussion why we need formal representation at all. So nowadays, AI in a popular media is very often a synonym for large language models such as ChatGPT or Llama or Claude and so on. And all these models use natural language as an input, right? You can input things into ChatGPT, and the output is also the textual input. So the question is, do we really need some other representation? Does it make sense to have a lecture on formal representation and on search in case we have large language models that basically we can talk to them or write them instructions using natural language? We can describe the problem using natural language. So why do we need some other representation? What do you think? Yes? Sorry? Speed? Yes. You know, like the AI that is slow is sort of double-edged sword, because the size of the problem is usually very, very large, and very large. And even in our cases, like we will have, you know, many states and many possibilities, and like finding the right solution in these possibilities is time-consuming. But like we will get to there, I would say, in fourth lecture. Yes, in fourth lecture, where we will like see the trade-off between if we have something universal, applicable everywhere, as is the topic that we will cover today, then we are able to like solve almost everything, but it can be slow. And then, like on the fourth lecture, we will have restricted possibilities. So we will pose some assumptions on how the formalization can look like, and we will not be able to solve everything, only some class of the problems, but we will be able to solve it faster, right? So like this is the trade-off with speed. When we are talking with, regarding the LLMs and like current AI models that are publicly known, the difference is slightly different than speed. So what are the problems of natural language? It's not exact. Yes? And can you be like more specific? Like, what do you mean that it's not exact? And anyone, you don't have to. Yes?
I think we can just translate the language, the input the user has, into some meaningful data that can be used in the model as an input.
Yes, you can do that. So you can basically do the transformation from natural language into some other representation. Yes, you can do that. But the question is like whether you need that other representation, right? Like you can take natural language and then have some other representation. Yes, like you can do the transformation. But my question is whether you need this. Yes?
Because the natural language is inherently contextual. So
Okay. Can you elaborate on that?
a lot of the meaning of the fictional words we say depends on the context. And usually in computers, we can't represent the context just from the exact text that was input.
Mm-hmm.
We need some way to store it and
Yes, yes, yes. Like exactly. I think this is like this was also my idea and my thought process when I was like putting together the slides. And like one of the disadvantages is that natural language is ambiguous in terms of like, as your colleague has like correctly pointed out, that we interpret the words in some context. For example, when, like, if you go working for some multinational corporate, you will find out that for us in Europe, Central Europe, or slightly to East Europe, when you say that something is awesome, that is truly awesome. For US colleagues, if something is awesome, it's, yeah, okay. Basically awesome, level of awesomeness, and if they say you that this is awesome, what they really mean that it's okay, right? So, like, the meaning of word is different, depends on context, on culture, and also like you can have words with like slightly different meanings. And when we make the description using natural language, it's like we cannot really like exactly know what's meant by that. Like, so for example, like you will be working with your colleagues, for example, in some company or on a research project, and then someone tells you, "Yeah, I've done this part. It's done." What does it mean? It's done. Does it work all the time, or have I just like run one successful experiment and it produced correct results? It was running 1 hour or 7 days. You know, like there are all these questions that we need to specify, and natural language is like generally not very good good for this. So another example that I have on the slide is, imagine that, and we will use example for a robot collecting golds in a maze, and you will be using that also in labs. So like when we want to specify like this goal for a robot, if we say that collect all golds in the maze, what does it mean? Can I collect them directly, and can I carry as a robot multiple golds, or or do I need to collect one, then put it somewhere else, and then collect another one? And what does it mean to collect? Do I need to be exactly on the gold, or should I be like next to it, and how far, right? So like there are all these questions where if we just describe it, it's not really like enough to properly solve the problem and answer the question. And you can also try to like use this with, for example, ChatGPT, right? So if you use, for example, GPT-4o, and which is standard language model, and you will prompt, like you can take the maze from the labs or from the lecture, and you can ask the ChatGPT to produce a plan to collect all golds in some maze, right? So ChatGPT-4o will basically output very confidently some plan, some actions that don't make sense at all, right? So basically it will go through the walls and so on. Similar thing happens if you want to like use these language models to play chess, for example. Like they are very creative in generating new pieces where they weren't before, and by this they are able to actually win quite a lot of matches because, oh, I have a queen here. Okay, cool. This is like this is the like natural thing that happens in these language models, and like we will get to these limitations more like towards the end of the course. Like if we don't have like proper formal representation, we cannot really avoid these kind of things. So that's why like the argument is that we really need some formal representation because it reduces the ambiguity, it reduces the uncertainty that we have about the definition of the problem, and we can have the algorithms that have guaranteed outcomes. So when we'll be talking about search algorithms, we'll be talking about other algorithms, game playing algorithms. So these algorithms will like work all the time because like when we will be designing chess playing algorithm or tic-tac-toe playing algorithm, it will not magically create new action because it's not possible to do so. Like we will have well-defined problem, we'll have limited options the algorithm can choose from, so there is no possibility for inventing new action. Any questions so far? This is like super important, right? Like I really want to convince you that it's helpful for us to think, to reason about the problem if we like write down a formal representation. Like right now, I haven't really specified what formal representation is, and we will get to that. But like in a very simplified way, imagine that you want to like implement solving it. Like you want to write a piece of code in Python, in C, in Rust, in whatever, right? You want to write it down somehow. You need to like capture the problem using a programming language. So this is a formal representation. Okay, so as I mentioned, search is really like one of the most fundamental and universal methods for solving problems. And if we have this formal representation, then like using search, we can look and find the solution, and we can look for the solution in some systematic way that makes sense and allow us to find the solution. And the formal representation is basically that we will capture all the configurations of the problem or the situation that can happen in the problem we define them using states. So we'll have some states, some set of states that will be denoted as capital S. And these states, like one state from this set, would be some configuration of the problem. So for example, when we will be talking about robot in a maze, it will be some, like, we want to capture like where the robot is placed and how the situations look like. If I want to capture this situation, then like you all here and your positions are part of the state, because this is some configuration of the scenario, of the problem. And these states can change, and the change is due to some action, and this action basically modifies some state. Typically, when a robot moves 1 meter forward, this is a change of a state. The robot changed the position, so the state has changed. And when we apply the actions to the states, then basically we create a new state. And usually we will be like capturing and thinking about these states and these problems using some graphs, because it's very natural. Like when you like think about this, I have some finite set of configurations, some finite set of states. So these states can be nodes in the graph, and by performing action, for example, A1 in state S, or say S0, we can get to another state, S1. By performing action A2, we can get to a different state, S2, and so on and so on. Right? So we will be thinking and searching through some graph, and this graph can be either generic graph or it will be a tree. Like we will see like what is the difference between that. So what is important and is highlighted in the box is that if I have definition like this, if I have if I'm saying that okay, I have some state and I execute some action in that state, I will get to another state, then in that state as a 0, I need to have all the information that I need to know that okay, I actually can execute action A1. And if I execute action A1, I will get to S1. I need to know this. So all this information has to be like, captured somehow, somewhere. And typically, like we need to have this information in that particular state. It cannot happen that, like unless we want to, that if I'm in S0, then I don't know to which state I get to. Like if I want to have some uncertainty, then this uncertainty needs to be exactly like captured and modeled, and we will get to that when we will be talking about MDPs. But basically, I need to know that this structure happens. I need to know that in S0 I have possible actions A1 and A2, right? So I need to know all of these things, which basically means that at the beginning, we are talking about problems that we know the rules of, right? Like we know the rules of the problem. We know that there are these two actions. We know that in state S17, there will be actions A4 and A5 and so on. We need to know this. We need to have this information. We are not discovering what's all possible. We know that we have this definition in advance. Okay. And another example to show you like the exact combination of large language models and symbolic reasoning and search is the result from last year, where Google team developed a model that they called Alpha Geometry. And they entered that system into Mathematical Olympiad, where it scored like second highest level compared to best people in the world, and the system was based on two things. One was a language model, and second was symbolic reasoner. Like you need to have both. Like you need to have that formal search that actually guarantees you the outcome. You need to have that formal representation that gives you that, okay, if this holds and this holds and this holds, then the outcome is this one, and it's deterministic, and it's given, and it's true, and it's always true, right? Like you really need this, and for this you really need to have the formal representation in the search. So this is, I would say, yet another example of the fact that, like, for very successful applications of AI, you really need to combine both of the worlds. You need to be able to combine and to utilize all the good and that is in the statistical AI, meaning mainly machine learning. So you will learn machine learning in other courses, but also when you need some guarantees, you need to be able to rely on that output. You also need some formal reasoning, some symbolic reasoning, some search, right? So ideally, you need to combine the two. So let's dive into some examples. So this is a very simple puzzle. It's a 1-to-8 puzzle where there are 9 squares, and you have numbers 1 to 8 and 1 empty square. And the goal is to rearrange the numbers such that they are like ordered 1, 2, 3, 4, 5, 6, 7, 8, and then there is the empty square. So you want to somehow rearrange them by moving them up, down, left, right, and so on, so that like you will reach this state. So how can we represent this problem? Like, let's say we want to implement this. How to represent this problem formally? Any suggestions? Yes? Mm-hmm. Yeah. So basically, like this will be, like general for all the cases that we'll be solving, where like these edges are always actions, right? So like right now, when I'm more asking like what would be the representation in here, I'm basically asking like how do we capture the state? How do we define it that this is a state? And then like we can talk, how do we define the action? Like what does it mean to execute some action, right? So like this is basically the question.
I would say that each vertex is the whole 3x3 matrix.
Mm-hmm.
And the edges are the changes.
Yes. So basically, yeah, like there is, like we see the depiction on the slide, and nothing like prevents us from using this as a formal representation. So we can really have like two-dimensional matrix with all the numbers 4, 7, 8, 6, 5, 3, 2. Right. So like this can be a representation of a state, and then the action can be like, how would you define the action? For example, like one action here can be what? Yeah, go. Mm-hmm. Okay, so for example, like moving 1 to empty square, right? Like we will need to come up with something more compact, but for now that's good. Right, and this is another state, right? Like this is one action, this is another state, this is the original state. Okay, so this is one possible formal representation. there can be many formal representations that we can create for some problem. Like there is not really just one correct formal representation when you are solving some problem. Usually you have multiple choices, and these choices then like affect, for example, how easy or difficult it is for you to generate possible actions. How easy or difficult it is for you to like compute or calculate like what would be the next state. Like you can have a very compact representation, and then like it would be very costly for you to like compute like how the next state would look like, right? So like there will be always a trade-off. When you don't have a compact representation, it can happen that like when you want to store all these states in memory, you will run out of memory. So there is always a trade-off. So when you think about like this simple example, what are other possible representations? Can we, for example, save one number? Sorry? Okay, so basically what you're saying, I'll try to reformulate. So what you're suggesting is that we will start only, or we will store only the original state, and then we will like capture the following states as the original plus history of executed actions. Yes. Okay, that's possible. And if we want to do that, can we somehow simplify this? Because right now I need to like remember which number to move where. So, yeah, go ahead. Sorry? The number would be enough, yes. Basically, like we know that there is only one 1, there is only one 2, and so on. There is only one 5. So maybe like we can cross this because, of course, like only one can be moved. Can we find something else? Can we decrease it even further? Because, for example, okay, like for 3 by 3 we have only 8 numbers, but let's imagine that we actually have, I don't know, 10,000 times 10,000 the puzzle, and we'll have all the numbers. So like then we will like need to represent this number like exactly, and we don't need to do that. Mm-hmm. So left, right, top, down. Mm-hmm. Is enough to represent which one we move. So we go up, we go left. Mm-hmm. So exactly. So if I reformulate again, basically we can represent it that not that we are moving the number 1 to an empty square, but we can represent it that we are moving the empty square to the left. And instead of having the number, we can have up, down, left, right. These are 4 possible actions, and we can represent them more compactly than like exactly remembering which number we want to move to the empty square. So this whole thinking process and like this exercise is mainly to like give you the idea that it's always good to think at least a little bit about how do we want to represent the states and how do we want to represent the actions, because as I mentioned, like in AI, basically the goal is to solve difficult problems, and difficult problem means that we have many of these states, we have many of these actions, and if we are wasteful in like what we put in the state, if we are wasteful, how we represent these actions and how to apply them, we will not get very efficient algorithms. We will not get the result in time, right? Because we will have really exponentially many of these states, and it's really important if you do some calculations and you want to optimize these calculations, because if these calculations are applied exponentially many times, then it's a difference between you waiting for 10 minutes or 10 years. It really matters. And it's not like we are not diving into theoretical informatics and complexity and so on, but from the really practical perspective, think twice when you are implementing the states, because it really matters. So couple of representations that we have on the slide. So instead of having 2D matrix, we can have 1D matrix. That's almost the same. We can also store not basically the squares or the values of the squares that we have them in the problem, but we can store the position of the numbers. So the position of number 1 is 1, position of number 2 is 3, and so on. So this is one way how we can also reduce by one number the state representation. But in this case, it's more complicated than, for example, to apply the actions, right? Because in the first representation, you know that the empty square that you want to move up, down, left, right, it's right here. You can see it, but in here you need to see okay, I have all these numbers on all these squares, and you always need to basically go through the entire array to find the empty square. In here, you can you need to do that only in the worst case. Good. So another example. Imagine that you want to implement some algorithm for a robotic arm. So you want to find the right path of that arm to actually catch something. This is again simplified example, but imagine that you want to solve this, and given the fact, or the argument is that the search is really powerful and universal, so we can use search and formal representation also to solve problem like this. So what can be the formal representation of such a problem? Yes. Exactly. Yeah. So these problems are very often represented as the angles of the joints. So you measure how what is the angle of this joint and this joint and this joint and so on. And this gives you the representation and the position of this arm in the space. And based on that, if you move one angle with one joint, you execute some action, you change the state, and you can then compute the correct changes in these angles, so that you can catch the desired object. So this is another example, and another example is chess, which seems obvious. What would be the obvious representation of chess? Matrix, and what would be the values in the matrix? Yes. So we can have basically the matrix. We can have positions of the pieces on the board and so on. So this is one possible representation. So is it enough for those of you who play chess? Is this representation enough? Who plays chess? Okay, cool. So, like, because for knowing answer to this question, you really need to know the rules of the game, right? So that's why I'm asking the players of the game. So is it enough? We know that. Like, we know the position of each piece, right? Like, we can either represent it as your colleague has said. Basically, we can have 8 times 8 matrix and have the position, or we can like remember position for each piece. So like we know the position. Yes. Okay. Like these rules are. We want to somehow like capture them when we want to generate the actions. It's just that we need to have all the right informations to generate like these actions from. And my question is whether we have enough information. Yes.
We also need state machine for who was the last one, who was the last on the page.
Mm-hmm. Mm. So generally, like in chess, this is not sufficient, not enough information. Yes? Mm-hmm, 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 mm-hmm. And you? Yes, like pieces, we definitely need to differentiate, or basically we need to know like that this is white rook, right, placed on A1. Like, yes, this is definitely like necessary. The notation is like we'll get to that. You're right. And yes, castling. Yes, this is a very good example. So yes. If that's different, right? Like, what does it mean worth? That's already like when you want to like devise a strategy, like you're like defining some like what would be a good move or a bad move. Like right now we are just describing like what's possible, right? But like basically we want to like know how to create this graph with all the possible states. And then what you're describing would be basically, okay, so like in this state, it's actually better to go here rather than here, right? But right now we're in a state that how to define it properly, okay? So, yeah.
We need to keep the moves in some way. Like, for example, we move a piece with ID X from position 1 to position 2.
Yes, so that's the representation of a possible action, right? It's very similar to what your colleague has said, and this can be here, and this can be also part of the state. So we already have this like discussion when your colleague has said in this example that we can have basically a starting state, and then history of played actions can be the part of the representation of the new state. And in chess, this is particularly true, as your colleague has said, because of all the like exceptions that we have in the rules in chess. So for example, castling is one good exception, where castle means that your king like goes from E1 to G1, and your rook goes from H1 to F1. This is one move, and it's called castling. And to execute this move before neither king nor the rook moved, right? So like none of these pieces have moved before, and then you can castle. But if you take the king, move it to, I don't know, E2, then move it back to E1, then you cannot castle anymore. But if we have the representation that we just know the current position of the pieces, we would never know that we cannot castle, because the king has already moved. So for all of this, either we will have like binary flags for all these like situations that we need to pay attention to, or we will have representation of the state really in the format of history of played actions. So we'll have initial state, which can be initial state, for example, on a chessboard, in a chess game, and then you will have history of actions that first player moves pawn to e4, right? And this would be like, this history of actions would be the formal representation of the state. Again, like, it's a possible formal representation. It's used one, really, you can use it. The main disadvantage is that, like, to get to current position, you know, to visualize the position of the pieces, you actually need to execute all those actions, right? So it's a trade-off, right? So you will exactly know what happened, but to get to the current position, you actually need to execute those actions. So that's that. But the main like reason for this representation using a history of actions is really that in chess there is one other rule that is very specific, and basically if you try to really remember these flags, you will be doomed. Do you know which rule I'm talking about? Yes? En passant is actually quite all right, because like en passant, like the flag is very temporary. You move one piece, one pawn by 2 squares, and then like your opponent can take it like on the invisible square. Like it's a very specific move, but that's not the main problem. So in chess, whenever one position is repeated 3 times, it's a draw. So whenever one position occurs for the 3rd time, the players can claim that it's a draw. And for this, like, imagine that you would need to keep, okay, I have been, like, this is the position that I'm currently in, and this is the position I'm currently in, and so on. And you need to remember all of that to check whether, oh, I'm in this position, I'm actually 2nd time or the 3rd time, and so on. So for all of these reasons, really, having the history of played moves is a really good representation of a state in chess. Okay, so we have like covered 3 examples, like how can we think and reason about the problems, and how can we capture these problems formally. And now we can like go deeper and talk about, like, okay, now we know that we can create some graph that we can like search through. So what we are searching for? Okay, we have graph, we can search. We cannot really, but we will get there. But what we are searching for? So what we are searching for is some goal state, right? Like, we are not searching just for the fun of search. We want to find some solution. We want to find some goal state, right? So in chess, we want to checkmate the opponent. In 8 puzzle, we want to rearrange the numbers. In the robotic arm problem, we want to capture the object, and so on. So we really like want to get somewhere. We want to get to the goal state. So we want to find that this goal state like exists and how to get there. So basically, we are starting in some initial state, and we need to find this path, right? This is the solution of the problem, because we have a description and definition what the goal looks like, right? Like, we know that, okay, checkmate looks like this because the other king is in check and it cannot like avoid the check in the subsequent move, right? So it's like well defined, but we need to find the sequence of actions how to get there, and this is our solution. Like, this path is what we are looking for. And usually, like, it's not enough for us to find a solution. Usually we want to find the best solution, right? Like, it's not always possible. We don't always want to wait for 10,000 years to find the best solution. Sometimes approximately good enough solution is good enough. But like, we aim for like some optimization. And what we usually do is that we have some either rewards or costs associated with the plan, with the actions. And in AI, it's like you can find both situations. Like in some of the literature and some of the areas of AI, it's more common to have positive rewards, and you want to maximize the reward. So a reward can be, for example, +10 for collecting a gold, and you want to collect all golds, so you want to maximize the reward. You want to have as much as possible. Another part of AI, another part of like computer science has costs, and you want to minimize the cost. You pay 1 for each move. You have a robot, and you want to collect all gold and come to finish, and you pay 1 move for every action. So when you are optimizing, when you are finding this plan, you want to find such that the cost is minimum. You're minimizing the cost. Some time ago, when we were putting this course together, we really tried to unify it, and then we found out that it's not possible, and we gave up. So basically, you will see both of these aspects throughout the slides, because really, like, the literature, like, and even if you like, go read a book, either it's Artificial Intelligence Modern Approach or the reinforcement learning book, like, you will see both. So it doesn't make sense for us to try to like steer it and hide it. Basically, like, there are both aspects and they are equivalent. You just need to pay attention, like, what is really currently the goal, whether you want to maximize the reward or whether you want to minimize the cost. So, as I mentioned previously, like, when we want to find this solution, and the situation that we are here right now, like in this course, is that we know the rules of the problem. We know how to generate this graph, and like, our goal is really to find just the path. And already this can be a complicated situation. Of course, like, you can have areas of AI that are focusing on learning how this graph looks like. And these are, for example, model-free reinforcement learning-based algorithms that are just trying to learn, like, how this graph can look like what are the possible actions. So we don't have that definition in advance. We are discovering the problem as we are looking for the solution. But this is, like, yet another level of complexity on already complicated problem. So since this is introduction to AI, right now we assume that we can construct this. And then in other courses you can dive into, okay, how can I actually construct this? Like, if I have a robot and I want to find a path in a cave, I don't need to, or I cannot really have all the time the map of that cave. I need to explore. So you will have another layer of complexity, but then you can always like combine the two, right? Like, you will always have some partial representation, and you can use that for navigating through that what you already know. So since we have this description, what we will assume for the most of the lectures is that we have a formal model, what we talked about so far. But just to give you also an idea, is that sometimes the problem is so complicated that it's really difficult to formally write everything down. So another possibility is to have a simulator. So some black box that you can like feed into like the initial state and the actions, and you observe like what's going to happen. Like, this can be also a case where like, it would be really, really time consuming for you to capture formally everything that happens in the system. So for example, like when you want to study how people are behaving in a city. For example, you want to study traffic. Like it's very complicated to define the rules for every person in Prague so that somehow you're able to capture, like, okay, if I now increase the time interval for red on IP square in one direction, what would that mean for the whole traffic? Right? Like that would be super complicated to calculate from this state to this state. But you can have a simulator where you just do that action and you measure it. So this is another possibility. So when we were talking about the examples, we were discussing, and I was like trying to emphasize that like, you can have many different formal representations, and you can always choose like which formal representation is better, depending on like what you need and how effective the algorithm would be. But like there are some classes and I would say established representations that are used for sequential decision making, and we will like describe them today. I will try to introduce them to you so that you know what they're about, and we will slowly go through these representations over the course. So for sequential decision making, which basically is really you want to execute sequence of actions to get to a plan. So all the robotics, all the games, like really everything where you need to make a sequence of actions, like these four formal models are like the fundamental models that you can like, go to, and these are Markov decision processes or MDPs, partially observable Markov decision processes, POMDPs, extensive form games or imperfect information extensive form games, and then stochastic games or partially observable stochastic games. The naming conventions in AI and in this sequential decision making are not great, right? And you will like I will explain this, and I'm not too happy with how these things are named, because stochastic games isn't really a good name for that class of games. Yes, they are stochastic, but that's not the feature that you want to emphasize. But I'm too little guy to change that, so basically I can just tell you so that you know like how other people are calling these class of games. So as I mentioned, like the point here for you is mainly to know these names, these terms, that these classes of problems, these classes of AI models exist, and how they are like distinguished. And then like we will cover MDPs, like POMDPs, extensive form games, really throughout different courses, throughout different lectures of this course. So MDPs, what are the differences? So right now we will go through them very quickly, and then we will dive into the specifics. So for MDPs, this is basically the model when you have one agent, one actor in the scenario, and this actor is able to perfectly observe the state of the world. So typically a robot in a maze, or all the cases that we have described, like the 8 puzzle or the robotic arm, all these can be represented as MDPs, right? I have perfectly observable state. I know what are the positions of the numbers in the square. I know, let's say now exactly what are the joint, what are the angles in the joints, and so on. So these are MDPs. I have only one actor that can change the world, and this world is basically perfectly observable. I know exactly that I'm in state S0 or S2, or I'm in the goal. I know that. partially observable Markov decision processes are different in the fact that we don't know exactly the state, right? And now, if we go back to the robotic arm, when we want to model it more realistically, when we are measuring the angle of the joint, we'll most likely have some error. Like when we are, when you will try to do some actual hands-on experience with robotics, you will find out that the sensors and measuring is always has always some error, right? There is always some imprecision. So when I'm measuring, for example, distance, I'm a robot and I want to measure distance to these tables, like there will be always some discrepancy. Like it wouldn't be exact, right? So there will be always some error. So like in partially observable Markov decision processes, the agent doesn't exactly know the state of the world. The agent knows something that we'll call a belief, and this belief is a probability distribution over possible states. So this is some likelihood that, okay, with some probability, I'm in this state, in some probability, I'm in this state, in some other probability, I'm in this state. Right? So this is a belief. I think that with 30% probability, I'm here, with 50% probability, I'm here, and with 20% probability, I'm here. Right? Its distribution has to sum to 1, but I don't know exactly where I am. So these are POMDPs. In ecstasy-form games, the main difference to the cases above is that the games are there are more agents that can act, that can change the environment. So in MDPs and POMDPs, we have one acting agent, one entity that can change the world. And in games, we have more than one. Usually we will cover 2, but in general you can have n, basically any number. What's important for games is that we model every agent, and we call them players in games. We model every agent or every player specifically because each one of them has their own goal. Like in chess, black wants to checkmate white, and white wants to checkmate black. Like if both want to checkmate white, then it would be a very simple game, and it wouldn't be very fun. So the fact that the games are interesting is exactly from this like unique goals, right? Like this is what's interesting. You can very often like try to capture the games using an MDP or a POMDP, where all the other players are something like an environment. So you don't really model them exactly how they reason, what they want to do, which goals they want to pursue, and you just like focus on your own plans. For some games, this is okay. For some other games, this is not sufficient, because you really need to think about what the other is going to do. So that's why like games, like when you really want to solve them as games, and you want to have guarantees that your strategy in the game is correct, you need to have different formal representation for them. So ecstasy-form games are games where like this game evolves in sequences, in time or in turns, and the main like feature of ecstasy-form games is that we have finite horizon, and stochastic games is like distinctive feature and difference from ecstasy-form games is that they have infinite horizon, which or they can have, like they don't have to, but usually they can have. And this is like what I meant, that the naming convention is not really like that great, because yeah, like there are stochastic events, but you can have stochastic events also in ecstasy-form games by using something that is called chance nodes. So like the fact that it's stochastic and not deterministic is not the distinctive feature. The distinctive feature is that stochastic games allow you to play for an infinite number of turns, which seems weird, right? Like who wants to play a game for an infinite infinite number of turns? But for many practical reasons and many practical scenarios, you don't really know when the game is going to end. Like in chess, it's clear, right? Like we are playing chess, now it starts, and at some point, like it will finish because like these are all the states, and we cannot really be playing forever. But for example, in security, like imagine that you want to design a system that is playing the game against the attacker in a computer network. Right? So you don't know when the game is going to start because you don't know when the attacker will start the attack. You don't know whether the game has ended and you lose, or maybe you will find out later, but you don't know like the precise state. You don't know like this is the beginning, this is the end. So you cannot really like model it as an extensive form game. You can model it as a stochastic game where you want to like preserve that your computer network will be intact. And you get some observations, your state and belief can change and so on, but there is no like, okay, now we are done and we are no longer protecting because the game has ended. No, like you always want to protect. The game is like continuing forever. There is no clear horizon, and that's why like this makes sense. Even though like of course we will not play really the game forever for an infinite time. We just don't know like there is no clear horizon that we can use to model the game. So these are like the 4 basic models, and I hope that it kind of makes sense to you that like why we are talking about these 4, because like you can see that like gradually we are enriching the model with a fundamental aspect. Like we start with something that is the simplest, which are MDPs. We have one agent and perfectly observable situation, and then we add imperfect information or partial observability for the agent. Then we introduce more agents, and then we allow these agents to play forever. So let's go deeper into MDPs. So as I mentioned, like the MDPs is basically something that we have already started to talk about without the definition of an MDP. So now we can like follow with the definition, where we will have a finite state of states, finite state of actions, and we have a set of rewards. So the rewards would be the thing that the agent is trying to optimize. And the interaction with the world and how the dynamics are captured is discrete. So we have some like clearly defined timestamps where like we start in some situation, let's say it's time t0, and in each time step the agent like receives the current state, selects some action, executes that action, and reaches another state in the next time step. So basically it's describing exactly here with the fact that like in here we haven't really like emphasized the rewards, but basically like we have some states that are connected together and form a graph. The rewards and the next state can be stochastic. So for the first lectures and labs, like we'll stick with deterministic transitions. So we will not have stochastic events in MDPs, but in general, MDPs allow us to model stochastic events. So when I'm, in robotics, execution of an action can be also stochastic because actuators don't have to work properly all the time. So for example, I'm a robot, I have wheels, and like my action would be move 1 meter to the front. So I can like move 1 meter, but actually like my wheels can like slip, so I can move 90 centimeters or 105 centimeters. So there can be some stochasticity, some uncertainty about like to which state I will get to. So instead of like having this, I can have S0, then action A1, and then I can have like different possible states that I can reach, and I have known probability for each of this transition. Right? So this is like what the formalism allows us to do, and that's why like we have this like probability that I will reach some state S prime, and I will get reward R for reaching that if I play action A from state S. So the fact that this is like formally, like when you want to capture it, you will define a probability distribution. The fact that right now, like we will be in a deterministic world means only the fact that, okay, like this probability distribution would be trivial because we'll have only one action and subsequent state with probability 1, and all the others will be 0. Right? But the formalism is rich enough to capture that it's also stochastic. Again, like different literatures, or in different literature, you can have like a different representation. Basically, in here, I put it all together, so both like the next states and rewards are modeled jointly with one distribution, but you can have two different distributions. Like you don't have to model it as a one distribution, you can have two, right? So like you will have one probability that you will reach some state S prime, and another probability that you will get reward R. Right? So like you can separate it. It's really the same thing. So these are MDPs. Let's go back to our examples, and we have touched a little bit on this when we talked. So we have a maze, and we have a robot in a maze. The hashtags are walls in the maze. The arrow is the robot, and the direction of the arrow is actually the direction of the robot. And we want to find the gold, right? So what can be good representation of the state? Yes?
The state can be the whole maze at the current location of the robot, and the goal in all the walls.
Yes, yes. This can be basically, as we see it, it can be representation of the state. You know, as we have some like very often things that don't change like throughout the states. So, for example, the maze itself doesn't really change. What changes is the position and direction or orientation of the robot, and whether we have collected the gold or not. Then, like we can like separate the two and have it somewhere elsewhere, so that we don't have to copy the same thing throughout all the states. It's just like enough to have the access to that information. So we can also have the state representation basically as a coordinates of the robot in that maze. So, for example, like we need to introduce some coordinating system. So let's say like this is, you know, like this position here is 0, 0, and then you can like exactly identify that yes, my robot currently is at row 2 and column 1, and it's facing down, and the robot has not collected any gold. So this is valid state for this problem. And then like we can have the dynamics, and basically like we can, you know, follow and define it exactly using MDPs. So what does it mean is that we specify like what is the probability of this state and this reward if we are in this state and play this action. So in here we are in this original state, so we are in coordinates 1, 2, we're facing down and we haven't collected the gold, and if we execute action move forward, then this state, which basically means that the robot will be here, is reachable with probability 1. Right? So like this is, I would say, slightly complicated, or at the first, slightly complicated way how to capture the fact that yes, robot will go down. And I agree that yeah, this looks too complicated. It's just that like we are using some formalization of MDPs, and we want to like fit the current problem into that description, because it will give us something, and we'll get to that. Similarly, like we can have another example of a transition where in the same state, if we execute action move backward, so we try to hit this wall, then like we will not reach this state, right? So the probability of that state, 1 down false, is a 0 if we execute in this original state action move backward. Okay, so as I mentioned, like it looks complicated. So why we are doing this? Like, why do we need this formalization? So it really gives us like complete and well-defined problem and description of the problem, because like when we need to like imagine that you need to define all these transitions, and if it's stochastic, all these probabilities for every situation. Like you cannot really say that, oh, it somehow moves and sometimes it fails, right? Like you can write that in natural language, but for MDP, you need to be exact. Like you need to exactly specify what does it mean that sometimes it fails, sometimes it works. What does it mean sometimes that it's 20% or 10% or 5%? So you really need to like formally specify. You need to specify what happens if I execute this action in this state. What exactly happens? Like how the state changes and so on. So if we fit it in, we will have really well-defined problem. We'll have well-defined inputs and outputs for the problem-solving algorithm, because MDPs are solved for 70 years. So over the years, many great people come up with many great algorithms, so you don't have to reinvent the wheel. And this is like one important aspect of using existing formal descriptions, not only in AI, but also, for example, in mathematical programming. You will have courses like combinatorial optimization or linear programming, where you try to capture some problem as a mathematical problem, as a mathematical program using just equations and inequalities. And if you do that like successfully, then you can download a solver from IBM or from some other company and use that, and you don't have to implement that algorithm, because like if your problem fits that formalization, you can just solve your problem in a very efficient way. So this is like one of the advantages of using formal representation, but not on like arbitrary formal representation, but one formal representation that is like well defined, and there are many solvers that are able to solve problems that are captured as MDPs, as POMDPs, as, for example, constraint satisfaction programs that we will touch on in 2 lectures. So there are many examples, and really, like, if you have a problem that can be represented using this representation, then really use it. Like, you don't have to spend several hours trying to come up with your own algorithm if you can solve it for free, quotes and quotes, because you still need to do the transformation of the formal representation. But still, like you can use that, and then you can focus on other parts, right? So it really like it's very helpful to try to build on what already exists. The other part that I want to highlight is that, like, if we have this representation, we can actually reason about the problem. Like, we know what's going to happen. We can try to find the optimal path. We can try to find the maximum reward, and we can really reason. Like, many or several language models now can reason, and I put the quotes there deliberately because they don't have this. They can generate in a natural language something that resembles formal description, but they don't really do reasoning in this symbolic form. You don't have the guarantees that the outputs of these reasoning models are correct. They are repeatedly doing and generating the tokens, but they are not really reasoning because they don't have that like semantic understanding of what's going on, and they don't have the rules how these states are connected together. So that's why, like when you try, for example, the reasoning models, sometimes it can work, especially like if that problem that you're trying to solve is very familiar to what the model has seen, or like it's especially in a language way, it's quite familiar. But when you try to rename, for example, like you can try a very simple blocks world problem that you will see, for example, in reinforcement learning courses, and you can try that with the language models, even the reasoning ones. And if you like rename it or play with it a little bit, you can easily break the model, and it will basically generate nonsense. But like if we have like the formal representation that corresponds to what we are trying to solve, we have well-defined goal, we have well-defined actions, we know how it fits together, then we can really reason about the problem. And as I mentioned, like we can use the existing algorithms to find the solution. So we don't have to reinvent the wheel if someone else already implemented these algorithms. And of course, like if you then design some new algorithm for solving this class of problems, so you can design new algorithm for solving POMDPs, then like you can, your impact can be much larger because you can solve almost all of them. So very quickly through all the other representations. So as I mentioned, in POMDPs, the main difference is that we don't know, or the agent doesn't know the particular state, and instead the agent has a belief, and that belief is a probability distribution over possible states. So this is the main distinction, and this belief changes as the agent receives observations. So typical example is that, like we'll have that in the next slide on a maze, is that I don't know where is the position in the maze, in the map, but I know that like I see, for example, a wall that is in front of me, right? So like this is my observation, and then based on this observation, I can change my belief. I can like assess that, okay, like if I see a wall in front of me, I can be only at certain places. I cannot be in a situation where there is no wall in front of me, right? So this is these are the POMDPs, and we will get to that at the end of the course, that this belief is exactly updated throughout the course of the problem. As the agent receives the observations, we recalculate the beliefs, and the beliefs change over time, and as the agent executes the actions. So for now, basically, it's important for you to know that, yes, the belief is the probability distribution over states, and it changes somehow to reflect new observations, but the exact meaning and description of how these beliefs are recalculated, we'll get back to that at the end of the course. So as I mentioned, in a maze, we can have the robot, and we can have the observations, which, for example, can mean that in this particular case, the robot can observe that there are walls behind the robot on the left and the right side of the robot, but in front of that robot there is a free space. So this is an observation that the robot can have. So extensive form games, as I mentioned, there are these are finite games where we have fixed horizon. So, example, chess and, for example, tic-tac-toe and so on. So these are sequential games with 2 or more players. In this course, we will have only 2-player games, and we will have only games that are, I would say, exactly opposite. So one player like can win, and then the other player has to lose, and vice versa. However, in general, you can have games where both players can win. So like these can be non-strictly competitive games or non-zero-sum games. But again, like these are more complicated, so we will stick to simple zero-sum games. These are, as I mentioned, finite. We can describe and show them, and we will like analyze them as search trees or game trees. And the rewards are in this context termed utilities, and these are defined only on the terminal states or in the leaves of the game tree. So this is like slightly different compared to MDPs and POMDPs, where we have rewards with the actions. But again, like one is transferable to the other. So it's just so that you know when you see the definition in the literature. And in general, we can have imperfect information, but like this again is more complicated, so we will not go into imperfect information games in this course, but in master's program in computational game theory there is okay, in computational game theory there are courses for solving imperfect information games. And finally, partially observable stochastic games are basically multi-agent extension of POMDPs. So whatever holds for POMDPs, like you will introduce more agents with more their own goals, and this is, I would say, one of the most complicated formal representation there is. Basically, what's very complicated is, as we described, that every agent has belief, so probability distribution over possible states in a POMDP. So in a partially observable stochastic game, the actions of the other also like affect what's going on in the game. So you have, or the agent has their own belief, but also they need to consider what is the belief of other agents, because they will be playing based on their belief. And so you need then to consider also what the other agent think what is my belief, and also and so on and so on. So like this is really complicated, and basically most of the algorithmical aspects. So if we want to compute, for example, optimal strategy in these games, like these are in general intractable. This is really like the most complicated, or one of the most complicated formal representations, and we very often like focus on subclasses or subparts of partially observable stochastic games, because like in solving true fully general partially observable stochastic game is basically very difficult. Okay, so how can we find a solution to a deterministic MDP? So as we mentioned, like we are finding the path from some initial state to the goal state, and we want this path to either maximize the reward or to minimize the cost, right? So like this is what we want to do, and this is basically the solution of the deterministic MDP. If we have stochastic events, it will be slightly different, and like we will get to that in reinforcement learning. But for search and for deterministic search, like having this sequence of actions is enough. So this is what we are looking for, and this is what we can like find here using this search algorithm. So this is, as I mentioned, like at the beginning, I wanted to like give you some unification or unifying view on different algorithms that you most likely know. And this is like the very simple schema of those algorithms. So we can start from some initial state as 0. We can apply the actions that we have available to get possible new states. We can choose one of these new states. We can go to that new state, check whether we are done or not, whether this is a goal or not. If it's a goal, then we are done. We have found our solution. If it's not, then we go back to step 2 and repeat. And this is a search algorithm. It's very simple. And there are a number of questions that, like, when you see these simple like steps that may arise. So first question is, of course, like, okay, I generate several possible steps. So how do I choose, like, which step, which state to move into? And what will happen if we get to a state that we have already explored? So for the first question, which state to generate, which state to choose from the generated states? Well, we have some goal. We want to maximize our rewards, so we want to select such a state that, like, currently maximizes our rewards, and this is a good, like, idea. However, we can make a mistake, right? Because, like, at the current moment, the state that immediately gives us the highest reward doesn't necessarily lead us to the goal state in the long run, right? So we cannot really, like, forget whatever happened before, and this is why in search we usually keep a list of states that are reachable and that can be further explored. So these are all the states that we know how to get to, and from this list of states we select then next state to explore. And this set is called open list, or also a fringe. And this is basically like a data structure that you can use for any type of search. And depending on how we build this data structure, we will arrive at the different algorithms. So if this open list, this fringe, is sorted based on cost or reward, and we will select every time new state to explore that would, like, optimize this cost or reward, we will get to uniform cost search. If we don't sort it and we put things at the beginning and we also take things from the beginning, we have depth first search. If we put things to the back and get things, our states from the beginning, we get breadth first search. So we have basically one search algorithm, and what we change is really only how we select the next state to explore, how we model and capture the list of states to explore. This is the fringe, the open list. We can vary from uniform cost search, breadth first search, depth first search, and we will, like, see other type of searches next week as well that are basically using the same idea, and we'll just change how this fringe looks like. Okay? I will quickly go through the rest because we have only, like, a few minutes. Any questions to this? Because this is quite important to understand that, okay, basically, like, this is, you know, one simple schema of search, and really depending on how we choose the next state to explore, we can arrive at different search algorithms. Is this clear? Any questions? Okay, so like, hopefully BFS, DFS, and all these algorithms are like, known to you, so I can, like, go through them very quickly. Basically, depth first search is not really complete. You can really rely that, like, you will find the solution, because you can eventually end up in an infinite loop. BFS is complete, and it will find shallowest solution, but it also costs you the exponential memory, and uniform cost search is very similar to BFS, and also it can find optimal solution. So basically, what we are really, like, building using this algorithm is the search tree, right? It's not really a search graph, because really it depends on the state of, or history of actions that we executed, and we get to some node, and for example, this node and this node can correspond to the same state in the problem. But first we, for example, generate action move forward, then move backward, and we are in the same state, right? So we can technically explore the same same state multiple times. And to avoid this, we can maintain a closed list. So basically, a list of states that we have already explored. We already like generated possible actions, put them in the open list, so we don't need to like explore them again. So this is closed list. I will move this limited depth to the next lecture, so we will like cover that next time. So I will finish basically with this, not to go too much over the time. So basically the question is, like to intrigue you for the next week, this schema that we have covered, it basically follows, yes, I start with search and I go and I'm trying to find the best path to go, but I don't have to do that. I can also start from the goal state. I have defined some goal state, and then I can try to like backtrack and try to find the path to the start. And what's very funny is that I can do both things at once. I can start from the start, I can start from the goal, and I have two parallel searches. And the question is whether there is some chance that I will meet in the middle. Because I don't have to, you know, like I can choose my states such that I will reach, for example, goal state using this path, and these two searches will never collide. But we'll see next week how to guarantee that you are actually, like, you will meet in the middle. So this is something that we'll cover next week. So thank you very much, and I apologize for being a little bit late.